Hi, Stu Schwartz from MasterMathMentor.com. This is video AB25. The topic is Indefinite Integration, and it covers the AB Manual, pages 152 through 155.
This video begins the second half of calculus, which studies integral calculus. Quickly, you will learn about integration and its relationship to differentiation, and see how the two interact to solve problems quite different than the related rates and optimization problems that you solved in the first half of the course. If you think about all the mathematics you've learned since grade school, you will find that you have always done the same thing. You've learned an operation and then immediately learned its inverse. You started with addition and then learned subtraction. You moved to multiplication and then learned division. You learned how to square a number, then you learned how to take its square root. You took a log of a number and realized that was the same thing as raising 10 to a power. Trig and inverse trig, raising an expression to the nth power, taking the nth root, were all operations and inverse operations. F of x and f inverse of x are inverses to each other. Let's continue the pattern. We've spent the entire first half of the course learning about the differentiation process. So let's now talk about the anti-differentiation process, which should undo the process of differentiation. So if we take y equals x cubed and take the derivative, we get 3x squared. If we take the derivative of x cubed plus 1, we get 3x squared. If we take the derivative of x cubed minus 4, we get 3x squared. If we take the derivative of x cubed plus 2 pi, we get 3x squared. So when we take the antiderivative, we should go back to the original expression. However, we have a problem because we do not know what the constant was. In the first one, there was no constant. In the second, there was 1. In the third, there was -4. In the fourth, there was 2 pi. So we will say that the antiderivative of 3x squared is x cubed plus c, where c represents a constant. Whenever you do this process, you will always have a constant.
So the correct notation for writing an integral will be the integral of f of x dx is equal to capital F of x plus c. Two things of interest here. First, the dx. The dx shows the variable of interest. It is similar to when we differentiate and we say dy dx or dy dt. It explains which is the important variable. Secondly, when we integrate, we get another expression. For now, we will call it capital F of x. And we do that to show that there is some sort of relationship between small f and capital F. But realize that this is just an expression using x. Finally, we have the plus c, which always is present when we have an indefinite integral. It is always tacked on at the end.
So the correct notation is the integral of f of x dx is equal to capital F of x plus c. We use dx to represent the variable of interest, just as when we integrate an expression, we say dy dx or dy dt. The dx says that the important variable is x. And when we integrate, we will get some other expression. We're going to call it capital F of x, and there's some reasons for that we will see later. We always attach the plus c. So let's look at 3 examples. So, since we know that the derivative with respect to x of 4x is 4, we would then say the integral of 4 dx is 4x plus c. Since we know that the derivative with respect to x of sine x is cosine x, then we would say that the integral of cosine x dx equals sine x plus c. And since we know that the derivative with respect to x of x squared plus 3x minus 1 equals 2x plus 3, then the integral of 2x plus 3 dx equals x squared plus 3x plus c. Note we do not say minus 1, because when we integrate, we do not know what that constant of integration is. It could be any number. It could be 0. It could be 1. It could be negative 1. We don't know. You may want to stop the video and go back to the first slide. The cartoon will now make sense. Because integration is the inverse operation of differentiation, every differentiation rule will have a corresponding integration rule. So the derivative with respect to x of a constant is 0, and therefore the integral of 0d dx is c. The derivative with respect to x of kx is equal to k, and therefore the integral of k dx equals kx plus c. The derivative with respect to x of k f of x is k f prime of x. We can factor out the constant. Therefore, the integral of k f of x dx is k integral of f of x dx plus c. Again, we are factoring out the constant k. The derivative with respect to x of f of x plus or minus g of x is f prime of x plus or minus g prime of x. The derivative of a sum is the sum of the derivatives. Therefore, the integral of f of x plus or minus g of x dx will be the integral of f of x dx plus the integral of g of x dx plus c. The integral of a sum is the sum of the integrals. Each integral has a constant, but when we add 2 constants, we get another constant. Therefore, we just tack on the plus c at the end. Our most important rule for differentiation was our power rule. The derivative with respect to x of x to the n is n x to the n minus 1. Therefore, the integral of x to the n dx will be x to the n plus 1 over n plus 1 plus c, assuming that n does not equal negative 1. This is the power rule reversed. If you take the derivative of x to the n plus 1 over n plus 1 plus c, the n plus 1 will come out in front, canceling with the n plus 1, and we are left simply with x to the n. In problems 1 through 15, you are given expressions and asked to integrate them. You should be able to do them in one step. It is recommended that you immediately take the derivative and determine if you get back to the original statement. That is always a good way to determine whether your integration is correct. In number 1, the integral of 7 dx is simply 7x plus c. In number 2, the integral of x to the 5th dx by the power rule is x to the 6th over 6 plus c. Take the derivative and we get 6x to the 5th over 6, which is back to x to the 5th. Number 3, the integral of x to the 12th dx is x to the 13th over 13 plus c. Again, taking the derivative, we get 13x to the 12th over 13, which is x to the 12th. In number 4, the integral of x to the 4th minus x squared dx is x to the 5th over 5 minus x to the third over 3 plus c. In number 5, the integral of t cubed plus t plus 1 dt. Now we're integrating with respect to t, so we get t to the fourth over 4 plus t squared over 2 plus t plus c. In number 6, the integral of 3x to the third dx, the 3 just sits there and we get x to the fourth over 4, getting 3x to the fourth over 4 plus c. In number 7, the integral of 2x squared minus 7x minus 8 dx is 2x to the third over 3 minus 7x squared over 2 minus 8x plus c. Number 8, the integral of 2/3 x to the fifth minus 7/3 x cubed minus x squared over 4 dx. So we get 2/3 x to the sixth over 6, which turns out to be x to the sixth over 9th, minus 7/3 x to the fourth over 4, which is 7x to the fourth over 12, minus x cubed over 3 times 4, which is x cubed over 12 plus c. Get used to working with fractions with integrals. They occur frequently. Finally, number 9, the integral of ex is ex squared over 2 plus 1 over e times x, because e is a constant, or x over e plus c. When we took derivatives, we frequently had to simplify them or transform them into another form to apply one of our differentiation rules. With integration, the same is true. Plus, using the power rules frequently creates fractions or complex fractions which must be simplified. As a result, integration involves more algebra, and you may need to review your rules on simplifying algebraic expressions, especially complex fractions. The 6 problems illustrate the work that must be done before and after applying the power rule. 10 asks for the integral of 1 over x squared dx. So to apply the power rule, we must write this as the integral of x to the negative 2 dx. And by the power rule, this is x to the negative 1 over negative 1, which is negative 1 over x plus c. We do not add on the plus c until the very, very end. In number 11, we must integrate 2 over x cubed minus 5 over x fourth dx. So first, we bring the powers upstairs and write this as the integral of 2x to the negative 3 minus 5x to the negative 4 dx. So this becomes 2x to the negative 2 over negative 2 minus 5x to the negative 3 over negative 3. It's very easy to make mistakes with negative signs here, so be careful. This becomes negative 1 over x squared plus 5 over 3x to the third plus c. 12 reads the integral of the square root of x dx. Our first step is to write that as the integral of x to the 1/2 dx. And by our power rule, this is x to the 3/2 over 3/2. This is where the complex fractions come in. This occurs quite frequently, so we flip the denominator and write that as 2/3 x to the 3/2 plus c. It should be very apparent that when you take the derivative of this, the 3/2 comes in front, which cancels the 2/3, and we're left with x to the 1/2 power. 13 reads 2 cube root of y minus 4 fourth root of y dy. So this becomes 2y to the 1/3 minus 4y to the 1/4 dy. Integrating, we add 1 to each of the powers, so we get 2y to the 4/3 over 4/3 minus 4y to the 5/4 over 5/4. And inverting the denominators and reducing, we get 3/2 y to the 4/3 minus 16/5 y to the 5/4 plus c. 14 reads the integral of 1 over the square root of x minus 1 over the cube root of x squared dx. Writing these with powers, that is the integral of x to the negative 1/2 minus x to the negative 2/3 dx. So by the power rule, adding 1 to each power, we get x to the 1/2 over 1/2 minus x to the 1/3 over 1/3. And inverting the denominators, we get 2 square root of x minus 3 x, the cube root of x, plus c. Again, it is a good idea to take the derivative of these and show that you will get back to the original expression. Finally, 15 reads the integral of x to the 2n plus n square root of pi dx, where n does not equal negative 1/2. N cannot equal negative 1/2 because we would then have the integral of x to the negative 1 power, and we will find that the power rule will not work there. We will work with that type of problem later. Also realize that n is a constant. We don't know its value, but it is a constant. So this simply becomes, by the power rule, x to the 2n plus 1 over 2n plus 1 plus n square root of pi x, because n and square root of pi are simply constants. And we then add the constant of integration. On the given chart, there are 4 rows, each containing 2 calculations. If you did not have a calculator, which calculation for each row would you prefer to do? As stated before, in math you first learned the operation and then the inverse. And the operation was always easier than the inverse. In first grade, addition was always easier than subtraction. And there were problems you couldn't even do until you learned the negative number system 7 years later. The same is true with multiplication. You could always multiply, but division ended up using remainders and fractions, which was learned later. Squaring was always possible, but square rooting involved a technique no longer even taught in school. And raising to a power could be time-consuming, but taking the log of a number can only be estimated. The same is true with differentiation and integration. Differentiation, while not always easy, is always possible. But integration can be difficult, and there are expressions that have no integral, like the integral of e to the x squared dx. There are 8 rules for differentiation, while there are over 100 rules for integration. For the basic rules we've seen, x to the n, we know that we have a derivative rule and we have an integration rule. For something in the form of f of x times g of x, for differentiation, we have the product rule. For integration, there is a corresponding rule called integration by parts, but you will not learn it until you take BC calculus. In the form f of x over g of x, for differentiation, we have the quotient rule, and there is no corresponding integration rule. In taking integrals, you sometimes have to be clever. For now, there are a limited set of rules. If an integration problem cannot be written as the sum of expressions with rational powers, you may have to change the expression so that it does. I call this a bag of tricks. And the more integration problems you do, the greater your bag of tricks will be. Here are 3 problems that illustrate that. Number 16 reads the integral of 2x minus 3 quantity squared dx. As with derivatives, when we encountered something like this, at first we had to multiply the expression out because we did not know the chain rule. There is a corresponding chain rule in integration, which we will learn soon, but will not always work. So in this case, we will multiply the expression out to get the integral of 4x squared minus 12x plus 9 dx, getting 4/3 x cubed minus 6x squared plus 9x plus c. 17 reads the integral of x squared plus 3x plus 1 all over x to the 4th dx. As stated before, there is no quotient rule. So we will divide each term by x to the 4th. I call that creating a split. We split the fraction into 3 parts. And this becomes the integral of x squared over x to the 4th plus 3x over x to the 4th plus 1 over x to the 4th, which is the integral of x to the negative 2nd plus 3x to the negative 3rd plus x to the negative 4th dx. Applying the power rule, we get negative 1 over x minus 3 over 2x squared minus 1 over 3x to the 3rd plus c. 18 reads the integral of 6x squared minus 11x minus 10 all over the square root of x dx. This is similar to number 17. We have to split it into 3 fractions, getting 6x to the 3 halves minus 11x to the 1 half minus 10x to the negative 1 half. And now when we integrate by the power rule, we get 12x to the 5 halves over 5 minus 22x to the 3 halves over 3 minus 20x to the 1 half plus c. So here are our trig rules for differentiation and integration. We know that the derivative of the sine function is the cosine function. Therefore, the integral of the cosine function is the sine function plus c. We know that the derivative of cosine x is equal to negative sine x. We could say that the integral of negative sine x dx is equal to cosine x. However, we normally say the integral of sine x dx is equal to negative cosine x plus c. We use these rules so often that they need to be memorized, and here's a good way of remembering it. Picture a clock where we have at the very top sine, to the right at 3 o'clock we have cosine, at 6 o'clock we have negative sine, at 9 o'clock we have negative cosine. If we follow the hands in a clockwise direction, we go from sine to cosine to negative cosine. The derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine is negative cosine, and the derivative of negative cosine is back to sine. So if we follow the clock in a counterclockwise direction, those are the integration rules. So the integral of sine is negative cosine, the integral of negative cosine is negative sine, the integral of negative sine is cosine, and the integral of cosine is sine. The other trig integration rules are based upon the trig differentiation rules, and while not used as much, they still must be learned. So the derivative of tangent of x is secant squared of x, therefore the integral of secant squared x dx is tangent of x plus c. The derivative of cosecant x is negative cosecant x cotangent of x, so the integral of cosecant x cotangent x dx is negative cosecant x plus c. The derivative of secant x is secant x tangent of x, so the integral of secant x tangent x dx is secant x plus c. And finally, the derivative of cotangent of x is negative cosecant squared of x. Therefore, the integral of cosecant squared x dx is equal to negative cotangent x plus c. Here are 6 simple integrals involving trig functions that you should be able to do in 1 or 2 steps maximum. Number 19 reads the integral of 4 sine x dx. The 4 just comes along for the ride. Our answer is -4 cosine x plus c. 20 reads the integral of -2/3 cosine x. Again, the -2/3 just comes along, and the integral of cosine x is sine x, so our answer is -2/3 sine x plus c. 21, the integral of 6 secant squared x. The integral of secant squared is tangent, so our answer is 6 tangent of x plus c. 22 reads the integral of 9 cosine x minus 4 sine x dx. This is 9 sine x plus 4 cosine x plus c. 23 reads the integral of negative sine x over cosine squared x dx. The way the problem reads, it's not one of our standard forms, but we can do some transformation into other functions. We can write negative sine x over cosine squared of x as -1 over cosine x times sine x over cosine x. And that becomes the integral of negative secant x tangent of x dx, which is negative secant x plus c. Finally, 24 reads the integral of 3 theta squared minus 2 cosecant squared theta d theta. This is a problem that mixes both regular functions and trig functions, and the integral of 3 theta squared is theta cubed, and the integral of -2 cosecant squared theta is positive 2 cotangent theta, and we add on the plus c. For all these problems, it is recommended, again, that you take the derivative and see if you come back to the original expression. Suppose we had an equation that stated f prime of x is equal to 4x. This is called a differential equation because it makes a statement about the derivative of the function. The goal of a differential equation is to find f of x, and that is called solving the differential equation. In order to do so, we integrate both sides. And we state that the integral of f prime of x dx is equal to the integral of 4x dx. The integral of f prime of x is simply f of x plus c1, and that is equal to 2x squared plus c2. But since c1 and c2 are constants, then a constant minus a constant is still another constant. So we say that our general solution to the differential equation is f of x is equal to 2x squared plus c. We call this a general solution because in reality it represents an infinite number of solutions, because any value c would make the statement f prime of x equal to 4x correct. Suppose we were also told that f of 0 is equal to 5. That is called an initial condition. We are giving some statement about the function at some value of x. From there, we could say that f of 0 is equal to 0 plus c, which we know is equal to 5, and therefore c is equal to 5. This gives us the specific solution of the differential equation, f of x is equal to 2x squared plus 5. Solving differential equations is complicated, and you will actually take courses in college just on solving differential equations. But in this course, we will solve some basic ones, as we will see in the examples. In problems 25 through 28, you are given differential equations and one or more initial conditions and asked to solve the differential equation. If you are given information about f prime of x, then that is called a first order differential equation. If you are given information about f double prime of x, then that is called a second order differential equation. In 25, you are told that f prime of x equals 3x minus 1 and f of 2 is equal to 3. We start by saying that the integral of f prime of x dx is equal to the integral of 3x minus 1 dx. And that means that f of x is equal to 3x squared over 2 minus x plus c. To find c, we plug in the value of 2, and we get f of 2 is equal to 6 minus 2 plus c is equal to 3, making c equal to negative 1. So our solution to the differential equation is f of x is equal to 3x squared over 2 minus x minus 1. You may want to check your work. First of all, look at f of 2, and you will find that that will equal 6 minus 2 minus 1, which is equal to 3. And finally, you may want to take a look at f prime of x, which will be 3x squared minus 1. 26 reads f prime of x equals x squared minus 2x plus 2, and f of 3 is equal to negative 1. To solve this differential equation, we state that the integral of f prime of x dx equals the integral of x squared minus 2x plus 2 dx. And therefore f of x is equal to x cubed over 3 minus x squared plus 2x plus c. Plugging in 3, we get f of 3 equals 9 minus 9 plus 6 plus c, and we know that's equal to negative 1, making c equal to negative 7. So our final answer is f of x equals x cubed over 3 minus x squared plus 2x minus 7. You can check your work just like we did in problem 25. 27 is a second order differential equation. F double prime of x equals 2, f prime of 4 equals 0, and f of 4 equals negative 1. Since we're given f double prime of x, we start by finding f prime of x, which is equal to the integral of 2 dx. That means that f prime of x equals 2x plus c1. Plugging in our value of 4, we get f prime of 4 is equal to 8 plus c1. And since we know f prime of 4 is equal to 0, we set that equal to 0. And therefore c1 is equal to negative 8, and f prime of x equals 2x minus 8. So now we can go back and take the integral of 2x minus 8 dx and say that that's equal to f of x. And therefore f of x equals x squared minus 8x plus c2. We use the fact that f of 4 is equal to 16 minus 32 plus c2, and we know that's equal to negative 1, making c2 equal to 15. So f of x equals x squared minus 8x plus 15. We can check our work. Plugging in 4, we get 16 minus 32 plus 15, which is negative 1. F prime of x is 2x minus 8, and therefore f prime of 4 is equal to 0. And f double prime of x, we know, is equal to 2. In 28, we have another second order differential equation. We're given that f double prime of x equals 2x, f prime of negative 3 equals 0, and f of negative 3 equals 10. We start by finding f prime of x, which is equal to the integral of 2x dx. So f prime of x equals x squared plus c1. And plugging in negative 3, we get f prime of negative 3 equals 9 plus c1, and that's equal to 0. That gives c1 is equal to negative 9, and f prime of x equals x squared minus 9. Therefore, f of x equals the integral of x squared minus 9 dx, or x cubed over 3 minus 9x plus c2. Now plugging in negative 3, we get f of negative 3 is equal to negative 9 plus 27 plus c2, and that's equal to 10, making c2 equal to negative 8. Therefore, f of x equals x cubed over 3 minus 9x minus 8. We can check our work first by plugging in negative 3, we get negative 9 plus 27 minus 8, which would equal 10. F prime of x is equal to x squared minus 9, and f prime of negative 3 is equal to 0. And finally, f double prime of x would simply equal 2x.
Number 29 reads, given that the graph of f of x passes through the point 0 pi, and that the slope of the tangent line to f at the point x f of x is 1 minus x, find f of pi. Students should realize that this is the same situation that they saw on the last slide, where you were given a number of differential equations to solve. This is a differential equation. You are given the fact that the slope of the tangent line at a point is 1 minus sine of x. That is a differential equation. F prime of x is equal to 1 minus sine of x. And if we're being asked to find f of pi, then we want to solve the differential equation for f and then evaluate it at pi. So we start with the integral of f prime of x dx is equal to the integral of 1 minus sine dx. And we end up integrating that f of x is equal to x plus cosine x plus c. Plugging in 0, we get 0 plus 1 plus c is equal to pi, making c equal to pi minus 1. Therefore, f of x is equal to x plus cosine x plus pi minus 1. And now at x is equal to pi, we get f of pi is equal to pi plus cosine pi plus pi minus 1, which is 2 pi minus 2. The graph verifies the answer. F prime of x is equal to 1 minus sine x is shown in red. And since f prime of x is at 0, somewhere between 1 and 2, we would expect that our curve f of x will level off somewhere in that interval, and it does. And since f prime of x is positive in the interval shown, then f of x will be increasing through the interval shown. Since f prime of x is decreasing between 0 and approximately 1.5, increasing between 1.5 and approximately 4.5, and then decreasing again, that confirms the concavity. The function itself is concave down, then concave up, and then switching back to concave down. And of course, the function also passes through the point pi, 2 pi minus 2. So far, we have only seen easy integrations, but integration itself can be very difficult. Just as we used the chain rule to allow us to take more complex differentiation problems, we will be doing the same with integration with a technique called U substitution, which will be shown in the next video.